Today we are just going to go directly to the Clifford algebra we will use, and that way we can start doing some more interesting exercises. So this is the Clifford algebra of the projective space remember that we said the projective space is you take your 3D space, you embed it in a 4-dimensional space, you put it at the fourth coordinate equal 1, and then intersecting rays through the origin with that space, you get all your entities. You can get point directions and so on. So the one we are going to do is the Clifford algebra with 0 vectors squaring to 1, 3 vectors squaring to -1, and 1 vector squaring to 0. Okay. Remember, to define the Clifford algebra, the first thing we have to do is to look at what is the underlying vector space, and this one is going to be the projective space. Underlying vector space will be P3, which remember is just a 4-dimensional vector space. And if you want a drawing to go with it, this is your R3, and now we put this R3 at omega equal 1 in our R4 space. So X, Y, Z, and omega, and then we should race through the origin, and then we get the entities in there. So this is P3, 4-dimensional space, basis vectors E1, E2, E3, E4. And now we need, in order to do the Clifford product or the geometric product, we need to use the outer product of Grassmann, and then we need to define a scalar product. So the scalar product that we are going to define in this vector space it's a degenerate matrix. Degenerate. I'm not muted, no? Degenerate. And it's given, remember we said any bilinear product it's given by a matrix. The matrix will be -1, -1, -1, 0. Which means when we measure distances, angles using this matrix, the fourth component is going to go to 0, because we really want to measure in this 3D space, which is embedded in the 4D space. It's degenerate because it has zeros here. Many people don't like metrics with zeros here, but they exist too. So this is our space. 4-dimensional space with this degenerate matrix is what will create our Clifford algebra. So now let's start operating. Remember that the Clifford product, if we had 2 elements, so given for instance a vector A, which will be A1 E1 plus A2 E2 plus A3 E3 plus A4 E4, so just a vector of this vector space. Now we have another B with the same structure. We can create the geometric product, which is equal to the scalar product AB plus the outer product A wedge B. And now what we are going to do is apply this to our particular space and our particular product. So applying this, apply geometric product to basis vectors, geometric product to basis vectors, we get that E1 square, which is E1 will be this plus 0, and this, if you look at this matrix, is minus 1. The same for E2, for E3, right? E2 square, E3 square equal minus 1. And then when we do E4 times E4, the scalar product gives 0, the outer product gives 0, so E4 square equals 0. So 3 basis vectors square to minus 1, one of them squares to 0. And then of course we have all the relations when you multiply 2 by 2, right? E1, E2 will be E1 dot E2, this will be 0 because they are perpendicular, they are orthogonal, will be E1 wedge E2, and that will be equal to minus E2 E1, and it's a new grade 2 or rank 2 element in the algebra. Same thing is true for all possible combinations. E1 E3 equal minus E3 E1, and so on. And then we can multiply 3 by 3, E1, E2, E3, right? E3, we can multiply E1, E2, E4, E2, E4, and so on. So we can do all the products of 3 of these 4 basis vectors, all possible combinations, and then we have E1, E2, E3, E4. There is one element of grade or rank 4. And doing these combinations, we get all the elements of our basis of our Clifford algebra. So the basis, the total, so we obtain let's see, I'm going to put all in one line, E1, E2, E3, the element of the vector space, then all the grade 2 elements, E1, 2, E1, 3, E1, 4, E2, 3, E2, 4, E3, 4, 1, 2, 3, 4, 5, 6, then all the elements of grade 3 or rank 3, E1, 2, 3, E1, 2, 4, E1, 3, 4, E2, 3, 4. Oh, I'm missing E4 here, sorry. E4. And then one element of rank or grade 4, E1, 2, 3, 4. And you can see that if you change the order, if you sweep 2 because this is associative, for instance, this is the same as minus E1, E2, E4, E3, and so on. So, you know, just swapping the vectors just gives you a change on sign, you know, if it's an odd number of permutations. Alright, so this is the basis of our space that we are going to use. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. So it's a 16-dimensional algebra. It's really big. Of course, you could write, a general element of this algebra, which would be a mix of multi-vectors or elements of different grades in this case, and you could write it as a linear combination of all these. But we are not going to use this algebra, it's too big. We are going to use half of it. We will use the even subalgebra. Okay? So let's just consider elements of even rank. So the one that would rank 0. And I'm going to organize it in a special way. You can organize it in many ways, but the one that I'm organizing it is the one we will use. So I want to start, okay, so we have the E2, E3, then we'll have E3, E1, E3, E1, E1, E2. Those have grade 0, grade 2, and now just the grade 4. E1, E2, E3, E4. Oh no, I'm forgetting the 4. Sorry. It is too small of an algebra. Okay, the fourth one will go with, okay. So E4, E1, E4, E2, E4, E3, E1, E2, E3, E4. Okay, now we have all the elements, and this is the order in which we are going to use them. 1, 2, 3, 4, 5, 6, 7, 8. So this is the 8-dimensional even subalgebra. So we call this CL plus, that means even elements, 0, 3, 1. So it's half of the algebra. And this is the algebra in which we are going to express rotations, translations, general displacements, lines, points, and so on. So if you want to compare to the transformation matrix, you have 12 elements there, plus a 0, 0, 0, 1. Here we have 8. And that's the reduction that we accomplish. So a general element Q will be Q0 times 1 plus Q1 E23 plus Q2 E31 plus Q3 E12 plus Q4 E41 plus Q5 E42 plus Q6 E43 plus Q7 E1, 2, 3, 4. That's a general element of the algebra. Now we don't want to carry this is something something here. We are going to just, as a notation, these unit vectors, we are going to give them a different name that relates to the Hamilton quaternions. So let me just put it here. And now notation. And let me make sure I have this one the same. Yeah, 1, 2K. Yeah. So E23, we are going to call it I. Remember that the unit I is square to minus 1, 2. E31 is going to be J. E12 is going to be K. And then E1, 2, 3, 4 is going to be epsilon. Now we need to name these ones, but if we did this right, we should be able to just put this as a function of these units. So for instance, E41, let's just not say, just in case we don't get it right, let's just multiply E23 times E1234. And this will be, there will be, I'm just going to put all the indexes together and then we swap twice, so we will have E23134, and this is minus E3134, this is E3314, and this is equal to minus E14, which is E41. Okay? So E23 times E1234 gives you E41. And this E23 times E1234 is I epsilon. So E41, we are going to call it I epsilon. And we should be able to do the same for the rest. So E31, E1234 will be equal to minus E3234, E3324, minus E24, which is equal to E42. E42 is going to be J epsilon. And then E43 is going to be K epsilon. Okay. K epsilon equal to E43 in the same way. So with this notation, and it turns out you can check this, that this is equal to epsilon K. Okay, so these particular two units can commute, not in general. Okay, same thing here. Epsilon J equal to J epsilon, epsilon I equal to I epsilon. So it's all just a change of notation. We want to go from this to something just with I, J, K, and epsilon. Then a general element becomes Q equal to, did I call it Q? Oh, BQ. BQ, yes. Extend a little bit more. Equal to Q0. Q1 was E23, which is I. Q1I plus Q2J plus Q3K. And now we have the I epsilon, J epsilon. Everything multiplies epsilon. Q4I plus Q5J plus Q6K plus Q7 that was multiplying only epsilon. So it's just another notation for the same vector, okay, with I, J, K, and epsilon. Now if we look at this, and just with the knowledge of Hamilton's quaternions, we can see that this is just two quaternions separated by the dual unit, at least the notation, right? And these units have the same properties: I squared equal to minus 1, J squared equal to minus 1, K squared equal to minus 1, IJ equal to minus Ji, and so on. Okay, so this can be seen as two quaternions, and by quaternions I mean Hamilton notation. Hamilton separated by a dual unit. Remember that the dual unit that we saw in the line geometry, epsilon squared to 0, is the same as this one. That's the dual unit. So two quaternions separated by a dual unit, that's what we call a dual quaternion. We call it a dual quaternion. So if you want to look at it from Hamilton's quaternions point of view, that's fine. I'm not saying that these are unit quaternions, that these represent rotations. I'm not saying that. They are just four-dimensional entities in which the units have those particular properties. Sometimes this algebra is also called the algebra of dual quaternions. So, you have the Clifford algebra of the projective space with the degenerate metric. Okay. It can be obtained with in a different way too. And this is the one we are going to work with. And let me say something else. Oops. Where are you going? Come here. Okay. We call it a dual quaternion. So we have the units, and we can, of course, just do the distributive property when we operate on dual quaternions with the Clifford product. It's useful to have the multiplication table. Remember, we can create the multiplication table. We can create. It's a big one. It's an 8 by 8. So we are not going to do it. We already did it with a couple of examples last day. But you have it in the notes. Okay. The notes are already posted on our Moodle page for this chapter, and let me just show it to you. The multiplication table that we are going to use, I put several. So depending on how you organize your units, you can get a different multiplication table. The one we use is 8.4. We use and it basically has this, E1, E23, E31, E12, and so on, and how they multiply together, which ones give 0, which ones give -1, which ones give another product. So given that multiplication table, you can create the general expression of what happens when you multiply two of these elements together. And you can have that program. It's just Q0 plus P0 plus Q0 times P0 plus So it's just when you do the distributive property and apply this multiplication table, you will get something that you also have in the notes, I believe. And it's big. Yeah, you have it in page 113. But there are some shortcuts. When you program, that's fine. But if you have to do it by hand, there are some shortcuts, and we are going to show those. Okay. We use 8.4, and then C general product general product in page 113. Okay. All right. Let's go to the next. Let me just give you a little bit more of notation, because we have a lot of different notations for these dual quaternions. One we already did, Q equal to, let's say, Q plus epsilon Q0. Two quaternions separated by a dual unit. Q would be equal to Q0 plus Q1i plus Q2j plus Q3k. Q0 will be equal to Q7 plus Q4i plus Q5 q5j plus q6k. When we use this notation, we call this the real part and this the dual part, similar to what we did with the lines. We can organize it this way. We can also organize the components in a different way. If we kind of assimilate this to a vector, ijk, the ijk components, and this to a scalar. So we can also write q as q0 plus epsilon q7, these are the scalars, plus, and now the vector part, we'll call this q plus epsilon q0. This 0 is down, that 0 is up, I know it's a little bit, and that's the dual vector. So you have a dual scalar plus a dual vector. It's another way of organizing it. Dual scalar dual vector, and now if we use this notation, we have q will be just q1i plus q2j plus q3k, and q super 0 q4i plus q5j plus q6k. Yes?
What is written in the dual vector?
The dual vector is these two vectors.
No, what is written there?
Dual vector, dual scalar.
No, that q plus
Epsilon q super 0. Okay, so this is a q, an arrow, and a 0 up there. So q0 with an arrow is a vector. It's kind of this one in which you just consider your vector part, the ijk. So dual scalar and dual vector. Let me just save it, just in case. Okay, dual scalar and dual vector. Real part and dual part, two quaternions, a dual scalar plus a dual vector. Different ways of looking at the same, is just a Clifford algebra element. So far we haven't put any geometrical meaning to this element, and that's what we are going to do next. Just for the displacement part, okay? So far this is just an element of an algebra. Now we are going to consider the unit elements. Unit elements. Are those that have length equal 1, and if you remember the quaternions, what we do in order to obtain the length is we do element times its conjugate, right? So unit if q times q conjugate is equal to 1. And if you remember, how did we do the conjugate? We just put the minus in the vector part, in the ijk, right? And then leave the plus with the unit, right? It's kind of similar to the complex conjugate, in which we just change the sign of the I part of it, right? So in this case, the conjugate changes the sign of the ijk. Let's just try, see what we get. So we are going to use probably better this notation. So this will be a plus, this will be a minus, basically. So So we have Q0 plus epsilon Q7 plus Q plus epsilon Q0. All this multiplied times, that's going to be long, Q0 plus epsilon Q7 plus minus Q minus epsilon Q0. Actually, I may want to use the other. I mean, this is good for developing, but probably this is better just to see the real and the dual. Okay, we can do this, or we can do Q plus epsilon Q0 times. Now when we conjugate, we will conjugate, this and this. The epsilon doesn't affect, so it will be Q conjugate plus epsilon Q0 conjugate. It cannot have more symbols already. Q0 conjugate. Okay, let me just put this up so that you guys can see it. Okay. So if we can operate here to get an easier solution. So it will be QQ conjugate. This is basically a unit quaternion if this is equal to 1. And then we have Q0 epsilon Q0 conjugate plus Q conjugate Q0. Okay, and we want this to be equal to 1 in order to be unit. And when I write a 1 here, I mean 1 plus epsilon times 0, okay? There is only real part. Which means what this implies is that Q conjugate has to be equal to 1. And then that other part has to be equal to 0. Q0 conjugate plus Q conjugate Q0 equals 0. So let me go a little bit up. Let me see. We have it here. We have the real part. This quaternion has to be unit, and then that. Cannot play too much with this. Okay. So that means that the real part is a unit quaternion. A unit quaternion. And we can probably develop this further, right?
So that means each of them can be 0 or...
These ones?
Yeah, or...
No, this gives you a relation between them. We could develop it, but okay, let's do it. It's going to be a little bit long. Okay, so Q, it's Q0 plus Q, right? Q0 conjugate is Q7 minus Q0 plus Q conjugate Q0 minus Q times Q0. Q7 plus Q0. Okay, this is what it says. Now you're going to allow me to do this product fast, but here you have to do a Clifford product. So take this element and then this ijk, multiply times this element and this ijk. Okay, we have taken out the epsilon, it's all ijk products. Okay. Okay, so Q0, Q7. This is going to be very long. Maybe we should just give you the result of this, right? Okay, this minus Q dot Q0, and I haven't explained how you do this product, so this minus, no, plus this plus Q7Q minus Q0 Q super 0, then this plus Q0 Q7 plus Q dot Q0, and then plus Q7 no, plus Q0 Q0 minus Q7 Q. Okay, so Q, okay, I know Q0 Q, this will cancel with that one, Q7 Q will cancel, at the end we get 2 Q0 Q7 plus 2 Q0 dot Q0. This is basically, if you take this element as your sorry, this is the upper 0, this is a vector, okay, dot Q0, this is equal to the first quaternion dot the second, twice, but the 2 we can take it out, so this is equal to Q dot Q0, and this has to be equal to 0. So these are the two conditions. So basically the real part has to be unit, and the real times the dual has to be equal to 0. It's similar to the conditions of the Plucker coordinates of a line. This is what makes unit an element of this algebra. Okay, this and then this one. But you can just, just say this is the condition for a unit dual quaternion, and it turns out, we'll have time, that is what represents our general displacement. Okay, and we can see that later, but a unit element of the algebra expresses a displacement. So let me just put the kind of similarity between the matrix algebra and the dual quaternion algebra. In matrix algebra, and dual quaternion algebra, so in matrix algebra, for instance, you have a rotation. It's a 3x3 matrix, right? And it has to be orthogonal. In dual quaternion algebra, a rotation is given by a quaternion, a dual quaternion, which is just Q plus epsilon 0. And this has to be unit. We'll talk about the translation, but let's talk about the general displacement. For a general displacement, we had a matrix T, which had the rotation in the upper 3 by 3. It had a translation vector or a position vector 0, 0, 0, 1. It's a 4 by 4, right? And the only condition is that this part has to be orthogonal, and then the 0, 0, 0, 1 in order to be a general displacement. In the dual quaternion algebra, a general displacement is a q plus epsilon q0, so that q dot q is equal to 1 and q dot q0 is equal to 0, and this is what we call unit in this algebra. And these are 4 elements, these are 8 elements. This is an element of the algebra. And how do we operate with these elements? If you want to transform a direction, or to transform, well, let's start with a rotate a direction. Rotate action on direction, on directions. With the rotation, you just multiply, right? V equal R times whatever direction you want. If you use the general displacement, which we can also do that, just put a 0 at the bottom, right? V0, just extend this a little bit, equal to T, little v0. And then action on points, we put a 1 there, right? Action on points P1 equal to T, little p1, right? With the dual quaternion algebra, this action uses the conjugation, and we saw that with the Hamilton quaternions. It's the same thing here. So if you want this v direction, what you need to do is q little v, q conjugate. That gives you a rotation. Another advantage of one of the advantages of this is you can transform lines directly. Here, if you want to transform a line, you know, a line is a six-dimensional entity, right? It's the Plucker coordinates. So you have to transform the direction and then transform the point and then assemble it again. There are ways of creating a mega matrix there and use that mega matrix to transform a line. Here you can transform a line directly. For a line, L will be equal to Q. I didn't put the hats, so let me just not put the hats. L equal Q, L, Q conjugate. So that gives you the motion of a line. And you can also move points and other stuff, but the difference is that in the matrix algebra, you have the right multiplication to transform stuff. In the dual quaternion algebra, you have this conjugation that you have to do, okay? Okay, let me see what else we want to say. Okay, let's just go in particular to how it looks. Any questions about this? We'll see a little bit.
The geometric interpretation of the dual quaternion expression.
Yeah, that's what we are going to do next. So the unit dual quaternion. I mean, dual quaternion in general is just an element of the algebra. Depending on the components and conditions, it could be, a displacement, or it could be a geometric object. But let's look at the unit dual quaternion. When we have a unit dual quaternion, it turns out that you can see, the Chasler's theorem right there very easily. We can write this unit dual quaternion Q as the following: cosine phi divided by 2 plus sine phi divided by 2 S. This would be like the first quaternion, plus epsilon minus t divided by 2 sine of phi over 2 plus sine phi over 2 S0 plus t divided by 2 cosine phi over 2 S. And we are going to write it also as a vector, as sometimes we did with the quaternion. And if you do that, you can just write, I usually write, as I told you, the scalar at the bottom, cosine phi over 2 plus f, and these are three components, right? Sx, sy, sc, corresponding to the I, j, k values of this vector. Sine phi over 2 S0 plus t over 2 cosine phi over 2 S minus t over 2 sine phi divided by 2. Alright. This is the way that we will usually express our displacement. Where we have here a dual vector, a line. We have S plus epsilon S0. Okay? S, let me just put it in here. S equal S plus epsilon S0 is the screw axis of the displacement. And if once you do homework 1, you will remember what this is. That means this is the rotation axis for your rotation part, and if you remember Chasler's theorem, every displacement can be seen as a rotation and a translation about and along an axis. This is that axis. Okay, it can be easily found in a dual quaternion. Phi is the rotation angle. And t is the slide along the axis. Along S. It's a rotation angle about S. So one of the advantages of using the dual quaternions is that it's very easy to find the invariance of the displacement directly from the expression of the dual quaternion. In a matrix, it's much more complicated. All right. So let me see if we want to start doing stuff with this or not yet. Yeah, let's just do some examples. So let's focus for right now in the elements in these dual quaternions that represent displacements, and then we will see which ones represent points, planes, lines, directions, and so on. So let's focus on this. Let's do some examples because I know you are already saturated. Okay, let's just do, I don't know, whatever you guys want. A rotation of angle theta about the z-axis, okay? X, Y, and Z. Our rotation axis in this case will be the z direction, right? So the line that defines the rotation will be 0, 0, 1 plus epsilon 0, 0, 0. It's just a rotation, so that means it's equivalent to, you know, a general displacement but passing through the origin. And that's it. So we just put these parameters here. S is 0, 0, 1, 0, 0, 0. The angle is theta, and the slide about the line is 0, because we don't have slide, just rotation. If we just write that there, we will get that this, let's just call it R, the rotation of theta, RC Z theta equal to sine of theta divided by 2 times S.
0, 0.
Can you see this? I don't want to extend too much, but let me just put it here in the side. Here. R Z theta equal to, we put first the real part, 0, 0, 1 times the sine, right? 0, 0 sine theta divided by 2, and then cosine theta divided by 2, plus, let me continue here, plus epsilon. S0 is equal to 0, so this part will disappear. T is equal to 0, so all this part will disappear, and then T is equal to 0. 0, 0, 0, 0. So we end up with the Hamilton's quaternion, as we saw it last time. That's a rotation about the z-axis, just that. If you want to write it not as components, but with our general formulation, that will be sine theta divided by 2 ijk, right? Let me just put the cosine. We put the one that multiplies the cosine theta divided by 2 plus sine theta divided by 2 k. That is a rotation about the z-axis. Let's see if I have some example with numbers here. No, we can do a general example, and then you will have also the examples of the notes. Is this clear? Yeah, kind of. Let me just put one more example, maybe. You guys can select what you want to do. Okay. What do we do? A rotation, a translation only. Translation? A translation.
And if we go with both translation and rotation, will it be difficult?
No, it's well, it depends on the numbers, because we'll have to multiply them, you know, unless it's on the same axis. Translation about and rotation along an axis, that's okay, it's easy. If not, we'll have to multiply. So
Let's choose the easy one.
translation or translation plus rotation. Okay, translation. Let's just give numbers of translation of t equal to plus rotation of theta equal pi over 2, 90 degrees, along and about s equal to, which axis do we want? Let's get the, and those are the Plucker coordinates of the axis, so you all know. What? Here, here, in the y, in the x, in the y. And where do we locate the axis? Anywhere. Let's just put it here, okay? And that's at 3, okay, in the z direction. So now we are going to rotate and we are going to translate about this axis. And now we need the Plucker coordinates of this axis. Direction 0, 1, 0. And then moment, we have to take the point, cross the 0, 0, 3, cross 0, 1, 0. And this is equal to 0, 1, 0 plus epsilon minus 3, 0, 0. You are faster than me. you have your practice already. Okay, so minus 3, 0, 0. Okay, and now we just need to go back to that expression, and then let's say this is a general transformation of along the y-axis of pi over 2 and 2. Now we take that. We had sine of the angle times the direction, so 0 sine of pi over 2, 0 cosine pi over 2 plus epsilon. We had the sine of the angle times s, so again the same thing, 0 sine pi. You have your expression in front of you, so you can do it, plus t over 2, the cosine of the angle, times s0, minus 3, 2 over 2, cosine pi over 2, plus 0, and then at the bottom was minus t over 2, minus 2 divided by 2, sine pi over 2. Okay. You see, even the easy examples, when it's, you have to do them in the board, this a little. So 0, 1, 0, 0 plus epsilon cosine of pi over 2 is 0, 0, 1, 0, minus 1. This is t. Or if you want to express it in using the units, we have j, right? J plus epsilon j minus epsilon, or epsilon j minus 1.
What is happening in this step? The middle one, yeah. No, the above one. Yeah.
Yes. What is this? This is, you apply, you see, let me go back. So you apply those values to your formulation of the general dual quaternion, which is a rotation about and a translation along your axis. So just putting your values there, you get that result. Now, if you need to do one displacement and then another displacement, composition of displacements, Clifford product. Composition, remember what composition of displacements was? That you first do a displacement, then you do another displacement, you want to know what is the overall displacement. Composition of displacements. Clifford, for instance, if we want to, why don't we compose the two that we have? Let me go back here. We have this rotation about the z-axis, this one over here, and then we had the rotation and translation about the y. What if we do, first we do this one and then we do the other one? What happens? Composition of this place. Oh, I lost the extension of the page. For instance, use in matrix form, we use just the matrix product. In the dual algebra, we use the geometric product. So we can do R z of theta times ty of pi over 2 and 2, and that will be, what was that, cosine theta over 2 plus sine theta over 2 k, right? K, Clifford product with j plus epsilon j minus 1, and just just operate with the units. Cosine theta over 2j, k times j equal, what is k times j? K times j is minus 1? I don't think so. K times j is k times j. K times j is minus, okay. K times j is I. No, k times j minus I. Oh, you guys know better than I do. Okay, thanks. jk will be I, so they go in the direct directions. K times j will be minus I, and so on. Should we do it? See what we get. We get cosine theta over 2j, and now we have plus epsilon, and now we have, yeah, same thing, cosine theta over 2j, and then minus epsilon cosine theta over 2, and then we have minus I, so minus sine theta over 2I, and that's k times j, and then we have k times j again minus I, minus epsilon sine theta over 2I, and then minus epsilon sine theta over 2k. The problem here is we took the translation equal 2, so you cannot see it. It is here. It's 2 divided by 2 equal 1. It's appearing here, but you cannot see that. Let's collect this. Let's just put it in our vector form. So we have a j. Do we have any other? We have an I, a j. That's it, right? So minus sine theta over 2 cosine theta over 2. We don't have a k, which doesn't have an epsilon, right? 0, and then we have an independent term. We don't have an independent term. 0. Am I forgetting something?
What about the k?
Which k?
The epsilon sine theta.
Yeah, the epsilon is coming here. Yeah, sorry. The epsilon is coming here. We are writing it as a vector like that. We have minus sine theta over 2 cosine theta over 2 minus sine theta over 2, and do we have an epsilon? Minus cosine theta. Is that okay? Not j, yeah, a cosine theta over 2j. So we have an I, a j, no, I, what is, oh yeah, here, an I, a j, a k, and then an independent term. Okay. That's what we get. Yes. We could just put numbers and see if this is correct. Let's just, yeah, we have a couple of minutes, so let's apply this for, let's say theta over 2 equal to what? Let's just do 0. Or for theta equals 0, so we actually just translate in the second one, in the first one. No, the first one will be 0. Let's just do theta equal to pi over 2 again. Theta equal to pi. Okay, I did something wrong. A rotation of pi. I prefer to change this. Remember that we have to put the rotation divided by 2. It would be pi over 4 in that case. So this is easier for our calculations. So rotation of pi gives this. All right, now we are okay. And now we put theta equal pi in this case, which was the first rotation about the z. Then we get this transformation equal to 0 minus 1 0 0 plus epsilon.
No, it's minus 1, the first one.
There's minus.
Good that you guys know how to do trigonometry. Okay, so pi over 2 minus 1 0 0 0 plus epsilon minus 1 0 minus 1 0, right? And we don't have time, but what we could do now is just see where a point goes in order to check our calculation. So if our calculations are okay, if we didn't make a mistake, then that is the composition of the two displacements. First, it's a rotation and a translation about an axis which is parallel to the y-axis, and then after that you do a rotation about the z-axis, and you get this transformation. All right, more next day.